How you doing? Starters today. But it's really a pretty simple system. I mean, there's only two wires on it. That's it. There's a big one and a little tiny one. Let me walk you through it. It's got some responsibilities that it has to do. Starter needs to turn the engine, the crankshaft, at the right speed. How fast is that? A couple hundred RPM. Maybe 150, 200. And it needs to do this efficiently. It's got during crank, before it goes strum, the stir part. If you want me to do it again, I will. Stir. It has to rely on all the current coming from battery. We've already talked about batteries. If you need a refresher, go back and look. But it needs to work within the amount of battery capacity that the car has. Now this is by far the biggest amperage draw on the battery is the starter, is the crank part. And honestly, it's just a pretty simple motor, and I'm going to be taking one apart and showing you what's inside of it in the next video. Please watch that. But really, it just the way it works is it has magnets in there, via magnetism. We have either permanent magnets, and what I mean by that is the magnets that are like stuck to your refrigerator, the pizza menu. It's always a magnet, or it has an electromagnet, which means it's only magnetized when it has electricity current flowing through it. And so we flow this current through the armature, which is a big heavy piece. The current flows through there, and that produces a magnetic field. And then we use, the magnets pushing against each other or pulling towards each other to force movement along this concentration. This field flux can be increased by looping the wires a few times. So we wrap the wires a little bit, and that increases our magnetic field. We also put it in a big heavy laminate iron core, and that helps focus the magnetic flux, the magnetic field lines coming out of the armature and the field coils. So how it works, we have these sliding contacts. They're brushes. They're called brushes, not the kind you brush your hair with, but these brushes slide along this commutator. I'll show you that next. That keeps the electrical contact while the armature is rotating. So we hit it with a current, positive and negative, simple motor thing. This armature, this loop in the armature, this guy right here, builds a magnetic field, and it either pushes or pulls off of the magnets that are on either side. This field has the same polarity as the stationary magnets. That causes the coil to start to rotate or start to slide on these brushes and on the commutator. So so how it works too. As the loop rotates, as the commutator rotates, as the armature rotates, the brushes slide along the contacts, keeping the current flowing. But it's reversing. It's getting ready to reverse the current because that commutator slides along the brushes. It helps, when it slides off the brushes, the magnetic field collapses, and it picks up the next brush in the armature. The inertia, the weight of this armature, the spinning many loops, keeps this guy rotating. They're very heavy. I'm going to show you when I take one apart. And then it just, it reverses contact on the loops, and it continues this rotation as long as there is current supplied to the commutator, to the brushes. So we got commutator, it's attached to the brushes, is attached to the current coming in. and it keeps the current flowing in the same direction, so it keeps it spinning in the same direction, and it keeps it spinning under power. And then we go back to square one and do it again. Now, there's this stuff called CEMF, which is counter electromotive force. It's produced in any DC motor, and it's AC current produced inside a DC motor. Remember when we spun the little motor, it produced some AC on the ATEC trainers. It's the same thing. So there's this AC ripple that is produced, generated by the motor assembly while it's spinning. There are ways to control this because that's detrimental to it. And as you can see, the CEMF goes up as the speed of the armature, the speed of the motor increases. And that causes the torque to decrease. So we get high torque right at the beginning, which is kind of what we need to start the engine because it's at rest and getting all that stuff moving. That's the highest work. That's the highest amperage draw. That's the place where we need maximum amount of torque. Once it gets rolling, and you guys live in Chicago, so you understand this, stir, rrr, 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 it starts to speed up. Anyways, I'll talk more about this in a minute. It produces this AC voltage, and it opposes the current flow through the motor. We can control this. There are certain types. There are series wound field coils, and what that means is there's just one path for them to flow in. You can see it through these. Here's the field coils. And this is just a coil of wire, more coils than it's showing on here. And then it flows to the brushes. So we have these brushes are then in series with the armature. So this whole thing is in series. These guys suffer from a lot of CEMF, but they have great torque right at the beginning. Anyways, parallel wound. These are less torque than series, and it spins a little slower. Smaller engines, less compression ratio. These series field coils, see, these are in series, and then these are in series. Here's our M line coming in. This is our battery connection point. But this doesn't go right to the battery. It goes to the solenoid. More on this in a minute. And they don't suffer from CEMF, but they spin slower and they have less torque. Here's a compound wound. This has kind of the best of both worlds. It does have good speed and good constant speed. It doesn't slow down, and it has decent torque. So you can see this M line coming in. There's a battery connection point. It splits again, and then one of these series field coils just goes right to a ground brush. So this is grounded directly. These three are grounded through the armature. And then we have permanent magnet motors. Now, these are the newer ones. It's a much smaller package. We have much better magnets now. So instead of using electromagnetic field coils like we've used in the past, it makes the starter bigger and heavier and, eats more current. These guys are smaller and lighter and don't. Now, here is the problem we have with these. Back in my day, if your starter didn't work, you tapped on the dang thing with a hammer. You can't do that on a permanent magnet motor because what happens is you smack it too hard and you'll shatter the magnets. And then it's done. It's done. You're done. You're not coming back from that. The starter's not going to work. You just junked it. It's a problem. And usually that's not where it needs to be tapped anyways. We'll talk about that in just a second. It has much lower current, these permanent magnet motors. Smaller package, they fit better. They're lighter. This is really pretty normal nowadays because of our technologies improved on these permanent magnets. Magnetic field's a lot smaller, so there is that. And they do spin a lot faster. Now, we can use that by putting in a gear reduction inside the starter. More of this in a minute. And then we have the movable pole shoes. This is old technology. I'll show you one of those when we get there. It's a lever used to move the pinion. They have a remote-mounted solenoid. And Ford was the only one that used it. A separate solenoid. We'll talk about it. Solenoid actuated. This is by far the most common. Almost everybody uses this type of system. There's a plunger and the shift fork right here. The shift fork is what throws out the pinion gear. That's the little gear that attaches to the ring gear to turn the engine. We have our big fat battery line that comes in, and then we got our M line that goes out into our starter housing. So big fat battery cable, heavy current, M line, heavy current, drops out. There's this plunger, and that's what throws out the pinion gear. Okay? That plunger also goes back, and there's a button back there. See this button right here, and then there's a spring, and then there's a heavy amperage contact disc. Think of it as the switch contacts. That completes the circuit between the B line, battery line, coming in, big fat, heavy current, to the M line. This is what completes this circuit. So they're usually mounted directly on the starter. They use it to engage the pinion, and then it's also used to deliver the high current to the starter motor. The other line that goes to this is the S line. More on this in a minute. So here's our permanent magnet guy. Should have taken these out of order. But it has a gear reduction, which it helps, they spin at a higher RPM, and we give up some of that RPM to gain more torque through the gear set. So we use this gear set, it's a planetary gear set, in order to reduce RPM of the starter armature and increase the torque. Smaller but a more powerful package. Read that as lighter, and anytime we can shave weight off is good for gas mileage. So components. We got the battery, we got cables and wire, we got the ignition switch that's attached to the S line, we got the neutral safety switch or a clutch inhibit switch. The neutral safety switch only allows the car to start in park and reverse. Park and reverse. Any other gear, it doesn't. That's so that dumb people can drive cars. And then we have the mechanical stuff: the pinion, the flywheel, the engine itself, the mechanical properties of this to look at. So we got electrical properties, and we have the mechanical properties. We good? I'm going to move over to watch the